All right, with this notes, we're going to start on buoyancy, and here we go. So buoyancy, and remember it's B-U-O-Y, buoyancy, not buoyancy. So buoyancy is an upward force on an object in a fluid. So what does that look like? Well, we have two different cases. We have submerged objects and we have floating objects. In the case of a submerged object, what we've got is our object here, and at some point it's going to have the buoyant force pushing up on it, and it'll have the gravitational force down on it. In this instance, we've got a square or a cube at some distance h1 below the surface, and the bottom of it is h2 below the surface. So what we're going to look at now is how the pressure is different on the top and the bottom. When we see this, we know that pressure increases with depth. As you go down, pressure goes up. So the pressure at the top of it should be less than the pressure at the bottom of it. Got my sign wrong there. P2 is greater than P1. Down here, it's going to be bigger than up there. So there's going to be some force caused by that pushes it up. So we remember that pressure is equal to force over area. So force is equal to pressure times area. So P1 times A, and pressure is equal to rho GH1 times area. Since it's a cube, the area should be the same on the top and the bottom. And our force 2 is going to be equal to P2A, which is rho GH2A. So what we find is that our buoyant force here is going to be equal to F2 minus F1, which is going to be equal to, basically, the only difference between these is H2 and H1. So it's going to be rho G delta H A. If we look closely, this guy right here is our volume of the fluid that's displaced. If we go over here, this is going to be the mass of the fluid displaced. And this is going to be the weight of the fluid displaced, also known as the force. In this first case, we notice that gravity is greater than the buoyant force, but in the case where it's floating, definitionally, we're going to have our buoyant force exactly equal to our gravitational force. Meaning that Fboy is equal to Fgrav. Before we move on with that, let's correct this formula down here, or simplify it, I should say. We have that buoyant force is then just going to be rho G volume. So rho GV. We can then use that up here and plug in. So buoyant force is rho GV, and that's going to be equal to mg. Yeah, mg. There we go. Now what we can do is solve. We can solve for our proportionality here. So this is going to be the buoyant force. This is going to be caused by our fluid over here. So let's write rho fluid times the volume of the fluid. Over here, m, we can break it down. We know that mass is equal to density times volume. So this will be the mass of our object times the volume of our object. And when we rearrange it, we can find the proportionality for our fluid, meaning that, well, here we go. Let's just write it out. We can rearrange this and make a proportionality. We can get that the volume of our fluid over the volume of our object is equal to the rho of our fluid, the rho of the object over the rho of our fluid. And basically, if our fluid is water, it's showing us specific gravity. So in that case, we have that rho object over rho fluid. In this case, that would be water, would equal our specific gravity. So it's showing you, this part right here is showing you how much of your object is going to be submerged into the fluid. So whatever fraction this is how far it sits down when it's floating. Notice that in this case, though, the fluid is just going to be displaced. The mass of the fluid displaced is going to be equal to the mass of the object that's sitting in it. It's going to keep getting pushed down until the force of it pushing down is equal to the force up. Well, force down is just weight. So the buoyant force is always going to be equal to the weight of the object that it's holding up as long as it's floating. Just a quick correction, this should be 28 over here. Now for 29, we're going to have a little bit of a thought experiment here. Let's say that I've got a bucket of water that I fill right up to the brim, and I've got a scale underneath that's going to weigh it. Then I've got another bucket over here that I fill up to the brim, same size bucket, same amount of water. They're both filled up to the top. But then I drop a block into this water, and it allows water to roll out of the side. It's already filled up to the brim. I want you guys to think about which one of these is going to weigh more. So which has higher force of gravity on it? Take a second, pause the video, think about it. We'll be back in just a second to answer that question. If you remember over here, we have that our buoyant force is equal to the gravitational force. So the amount of water that it's displacing is going to be exactly equal to the weight of the block. So if we look over here, on this left side, we should have just the bucket. If we want to look at the forces of it, this is just going to be for bucket plus for water. In this one over here, we're going to have the force of the bucket plus the force of the water minus the force of the water displaced. So that's the water that fell out, plus the force of the block, where these two are exactly the same. So if we add and subtract the same number, it should cancel out. The amount of water that gets displaced is going to be exactly equal to the weight of the bucket. Now, let's try a slightly different one. In this one, we have two buckets just like before, both filled up to the brim, both on a scale. Ooh, what the heck is that? Both on a scale, both filled up to the brim. But instead this time, I'm going to drop a steel ball into the bottom of this one. Just like before, water is allowed to flow out as volume gets displaced. I want you guys to take a second, think about it, which one of them is going to weigh more. So in this one, the one that weighs more should be the one with the steel ball. In the case where it's floating, it's going to displace the exact amount of water of its mass. And that's because it has to hold that force up for it to stay floating. The forces have to be balanced out. In this case, because the steel ball is more dense, it's just going to go straight down to the bottom. That means for the same volume, because rho steel is greater than rho water, the volume displaced by the steel is exactly equal to the volume displaced by water. But because the steel has a greater mass, that means has a greater density, it's going to have more mass for that same amount. So now I have more gravitational force. I've got the bucket minus the water. It's the same thing as up here. If I change this to the block, I change this to the steel. But in this case, F steel is greater than F water displaced. So in this case now, we have a heavier bucket because that steel's in it. And you guys should, if you want to try this out, you can do it with like a cup. Drop some ice in, and then try to find something that's like the same weight as the ice that's going to sink. You'll be able to feel it, especially if you make it a little bigger. let's do a problem with this. Let's say you're deep ocean fishing and then you find a multi-million-dollar statue at the bottom of the water that you're trying to bring back up because it's from an ancient civilization and you're trying to make it rich. Let's say it's about 70 kilogram statue. And let's say it has a volume of approximately, I don't know, let's say 3.0 times 10 to the fourth cubic centimeters. I don't know, just some number. We want to lift it up from the bottom of the water at a constant velocity. We don't want to have any acceleration on it that puts too much tension on our winch. So we want constant velocity. And we want to bring it up from the bottom. We're going to say it's slow enough velocity that we don't have to worry about drag underwater. I want to know what force do you need to lift it up, and I'll give you one variable, that the density of the ocean, it's slightly higher than normal water. It's about 1,025 kilograms per cubic meter. All right. I'm going to give you guys a little bit of a head start. I'm going to help draw the free body diagram for you. So upward, we're going to have the force of our winch. And downward, we're going to have the force of gravity. And our winch is going to get a little bit of help. I want you to figure out what is the last force on this free body diagram. Pause the video, try the problem out, and then come back. Remember, we're trying to figure out what is the force the winch needs to use to come up so that we don't put any acceleration on the statue and break any parts off. And yeah, good luck. So you'll notice the missing force that we didn't have was buoyancy. That buoyant force is going to be pushing it up, but it's not going to exceed gravity. That's why it sinks. You can't displace any amount of water that is going to lift that up because it's more dense than water. So what this tells us is that our buoyant force plus the force of the winch should cancel out gravity if we want to accelerate up, if we want to go upward at a constant velocity. We need a net force of 0, so this has to equal that. Well, I want to know the winch, so let's solve for the winch. That's going to be our gravitational force minus our buoyant force because it's the amount is being pulled down plus the amount the water is pushing it up. Let's go ahead, take a second, pause it, plug in what formulas you think we're going to need for those two things. So gravitational force, this is a physics 1 thing, is just going to be mg. And our buoyant force, this is the new one we learned, is going to be rho gv, or rho vg, however you want to write it, whatever sticks better in your brain. Here we go. So the mass of our object is 70 kilograms. And we're just going to use a solid 10 meters per second squared. If you want to use 9.8, go for it. Now remember, for buoyant force, it's the density of the fluid that it's in. It's the amount that it's displacing of the fluid. So it's that mass of water that was there, the gravitational pull down on it, that is now pushed out of the way that's lifting it up. So it's the mass of the seawater. Kilograms, oops, almost forgot. Times 10 to the third kilograms per cubic meter. And that's times the 10 meters per second squared. And the volume, we need to be in cubic meters. So I want you guys to take a second. This is part of the math review, being able to do conversions. Take a second, try it out, solve for it, and we'll come back together. I'll explain a little cool way to do it. I bet most of you don't know how many cubic centimeters are in a cubic meter, but you do know how many centimeters are in a meter. So a shortcut that I like to use with this, we have 3.0 times 10 to the fourth cubic centimeters. Instead of trying to do the conversion, what I just do is there are 100 centimeters. I'm trying to cancel out this per 1 meter. But again, I want to get to cubic. So all I do is I just cube it. There's 100 centimeters this way by 100 centimeters this way by 100 centimeters that way. So when I plug all that in, I find that my volume should be around 0.03 meters, cubic meters, 0.03 cubic meters. I come down here, I plug it in, and what I find my my winch force to be, when I put it all in, I'm going to get about 700 newtons for my gravitational force, I'm going to get 307.5 newtons. And when I solve, I get that I need 392.5 newtons to lift it up. You'll notice it's lighter than it would have been in the air. That's the same thing that happens to us with the density of the human body. You tend to, when you don't have like your air completely full of lungs, you tend to weigh about 1/6 of what you would on land. And that'll about do it for buoyancy notes. If you have questions, make sure to email me or ask in class.